This will be a modified version of the material normally covered in CS 230. In Module 1, we started looking at our computer from the bottom up. We started by looking at logic gates as the building blocks for our computer system. As we move away from this physical reality, we introduce levels of abstraction. The first level of abstraction was the introduction of bit sequences. We use zeros and ones to represent the reality of plus 5 volts or 0 volts within the hardware. Then we discussed different ways we could interpret those bit sequences, including as data or machine code instructions, for example. In Module 2, we moved up another level, away from bit sequences as instructions that would be executed by the CPU, to use a simple language, more human-friendly language, assembly code. In Module 4, we move up yet another level to a high-level programming language. We have experience creating code at this level prior to CS 230. This module will take a look at how we go from a language like Python or C to machine code. For this offering, we will focus mainly on the parts of the process that take us from a high-level language to assembly code. Here's an overview of the classical tool chain that takes code that is written in a high-level programming language such as C and eventually produces executable machine code instructions. All of these steps, the compiler, the assembler, the linker, and the loader, are programs that translate our programs from one state to another, eventually producing instructions that can be executed by the CPU. We often find these elements bundled together in an integrated development environment, also known as an IDE. If you've written a program using an IDE and then pressed Run to start its execution, the program is essentially moved through all of these steps automatically. We start with source code that's written in a high-level language, for example, Python or C, that is much closer to natural language than assembly code, and definitely closer to natural language than machine code. A compiler takes the source code and generates assembly code. This short description belies the complex process that is actually taking place. The creation of compilers by people like Grace Hopper made programming computers significantly more accessible. Assembly code consists of relatively small number of simple instructions. Generally, it takes multiple instructions at this level to handle a single instruction from a high-level language. In this course, you have essentially been acting as a compiler whenever you've written assembly code, probably thinking of an algorithm at a high level and then doing the translation in your head to create the actual assembly code. Assembly code is then read by an assembler and then converted into something called an object file. In our experience, this is what binasm does for us. The instructions in an object file are bit sequences. The number of instructions in an object file is comparable to an assembly code set of instructions. There is a little bit of extra work the assembler needs to do though, including translating labels into numeric values. There are two major categories of labels: those that would use relative addresses, that would be used in things like branching instructions, and those that use absolute addresses, labels that would be used to identify subroutines, for example. Very often our programs are not just a single source file. In many programming languages, for example in object-oriented languages, there are multiple files that work together, that need to be linked together to form a single process. We also may have files provided by an external library that we want to include in our program. At the time we link object files together, we need to deal with absolute addresses in particular in our machine code instructions, since blocks of code from the different object files will be moved into relatively new locations in memory. The final step is loading the code into main memory. This may include objects files from a library at this stage as well. After we've loaded it into main memory, the code can actually be executed. There are other execution approaches besides a compiler. It is not the only way to translate a high-level source code into executable code. Where a compiler will take source code and produce executable file before the program is run, an interpreter will execute the source code directly after you press run. A language like Python normally uses an interpreter, but there are Python compilers as well. Generally, compilers are thought to execute code faster, and interpreters are thought to be more helpful in debugging code since there is a more immediate reaction to errors at runtime. As with any design decision, there are trade-offs. Bytecode is an intermediate binary representation that would be akin to MIPS code that we've seen. Java is a classic example of a language that uses bytecode, whereas MIPS is strongly coupled with the CPU that will be executing the instructions. Bytecode is more closely connected with the source code. There needs to be an intermediate step that allows the bytecode to be executed on a particular machine. With Java, this step is managed by something called the Java Virtual Machine, or the JVM. So Java bytecode could be provided by a remote server and be interpreted by a JVM on a completely different machine. In fact, the fact that many web browsers had a JVM embedded in them is one of the reasons that Java became popular at the time that the internet became popular. Just-in-time compilation, or JIT, is a combination of interpretation and compilation. Basically, JIT compilation interprets the source code once, but if there's code that's executed more than one time, a bytecode instruction is translated into machine code only once, and it does not have to be translated again. This means that code that is repeated will run faster. As we move forward, we will focus on some of the steps handled by the compiler.